Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about Hamiltonian Formalism and Poisson Bracket Part 1 from the paper Classical Mechanics. So students, let us see what we are going to learn in this module. In this module, you will learn to write down the equations of motion in terms of Poisson bracket. And you will note a very striking similarity between the equation of motion expressed in Poisson bracket and the Heisenberg's equation of motion in quantum mechanics, which you have learned in your course. You will also learn that if the Poisson bracket of a dynamical variable with the Hamiltonian of that system vanishes, then that dynamical variable is a constant of motion. We saw that Hamiltonian formulation in general does not lead to any simplification in the solution of a problem. Instead of one second order differential equation in the Hamiltonian formalism, we have two first order differential equations for each degree of freedom, and in order to solve that we come back to the same equation. So one normally in this formalism has to reckon with the same equation of motion as obtained by using the Lagrangian formulation, and there doesn't seem to be any simplification. However, the Hamiltonian formulation leads to a deeper understanding of the structure of mechanics, and it plays an essential role in statistical mechanics and in quantum theory. And Poisson bracket, which is based on Hamiltonian formalism, that plays a key role in the transition from classical mechanics to quantum mechanics, as was first noticed by Dirac. Hamilton's equation in classical mechanics expressed in the form of Poisson bracket are very similar to the Heisenberg equations in quantum mechanics. We will first define Poisson bracket. A dynamical system is specified by the canonical variables it depends on, namely the generalized coordinates q1, q2, qn, etc., and their conjugate momenta p1, p2, pn, where n is the number of degrees of freedom. So a dynamical system is specified by giving it its conjugate coordinates and conjugate momenta, where the conjugate momenta are obtained, as we know already, from the Lagrangian through the relation that pi is the partial derivative of the Lagrangian with respect to the generalized coordinate qi. Now let capital G, which is a function of the conjugate coordinates of momenta and maybe of time t also, be any dynamical variable of dynamical system. So we have a dynamical system which is represented by canonical variables qi and pi, and we have a dynamical variable capital G which is a function of these canonical variables. Now the temporal development of this variable, that is dg by dt, the total derivative of this dynamical variable with respect to time t, is given by the chain rule, namely dg by dt is equal to sigma over I, partial derivative of g with respect to qi into qi dot, plus the partial derivative of g with respect to pi multiplied by pi dot, sum over all the i's, plus the partial derivative of g with respect to time if it depends explicitly on time. Now we can use the Hamilton's equation for qi dot and pi dot. Qi dot is dh by dpi and pi dot is minus dh by dqi. So using these expressions for qi dot and pi dot, the temporal development of the dynamical variable g becomes dg by dt is equal to sigma over I, partial derivative of g with respect to qi multiplied by the partial derivative of the Hamiltonian with respect to pi, minus partial derivative of the dynamical variable g with respect to pi multiplied by the partial derivative of h with respect to qi, plus a term which is partial derivative of the variable g with respect to time. Now this expression, which you can See within the brackets, this is defined as the Poisson bracket. This is a Poisson bracket between the dynamical variable g and the Hamiltonian h. That is the Poisson bracket defined and written as g comma h and is defined as sigma over I partial derivative of g with respect to qi multiplied by the partial derivative of h with respect to pi minus the partial derivative of g with respect to pi multiplied by the partial derivative of h with respect to qi plus a term which is partial derivative of g with respect to t. We can now define the Poisson bracket of any two dynamical variables a and b in the manner in which we have defined the Poisson bracket between the dynamic variable g and h, namely the Poisson bracket between two dynamical variables a and b is defined as the sum over I, the partial derivative of a with respect to qi multiplied by the partial derivative of b with respect to pi minus the partial derivative of a with respect to pi multiplied by the partial derivative of b with respect to qi, and obviously the Poisson bracket between a and b is equal to minus times the Poisson bracket between b and a. Some simple properties of the Poisson bracket can be easily seen. If c is a constant, then the Poisson bracket of a constant times a with the b is equal to the Poisson bracket of a with b multiplied by the constant c itself. Is simply equal to the Poisson bracket of a with respect to c plus the Poisson bracket of b with respect to c. And obviously when a is equal to b, the Poisson bracket between the two identical variables, that is a comma a, is equal to 0. The Poisson bracket of a dynamical variable a with a constant c is again 0 because the derivative of c with respect to qi and pi both vanish. If we have three dynamical variables a, b and c, then the Poisson bracket of the product of a and b with c, which is defined as the partial derivative of the product ab with respect to qi multiplied by the partial derivative of c with respect to pi minus the partial derivative of the product of ab with respect to pi multiplied by the partial derivative of c with respect to qi. Now this can be expanded and we can see that this can be written as the Poisson bracket of a with respect to c multiplied by the variable b plus the variable a multiplied by the Poisson bracket between b and c. Notice that in deriving these relations, we have used the fact that dynamical variables commute among themselves. This is certainly true of dynamical variables in classical mechanics. What is the meaning that they commute? The two variables commute if the product AB is equal to the product BA, which is certainly true of any dynamical variable in classical mechanics. But in quantum mechanics, the dynamical variables are treated as operators, and these operators do not commute in general. If the dynamical variables are the generalized coordinates and conjugate momenta themselves, then their Poisson bracket can be very easily seen to be of the form that the Poisson bracket between two generalized coordinates which are different qr, qs is equal to 0. The Poisson bracket between two momenta are also equal to 0. So, since q's and p's are independent variables, therefore, the partial derivative of q with this, see in Hamiltonian formalism, generalized coordinates and conjugate momenta, that's q's and p's are independent variables. Therefore, the partial derivative of q with respect to p or the partial derivative of p with respect to q is equal to 0. Therefore, the Poisson bracket between the coordinates and conjugate momenta QRPS, which is given by the expression sigma over I partial derivative of QR with respect to QI partial derivative of PS with respect to PI minus the partial derivative of qr with pi and with ps with qi, you can see that in the second term, since q's and p's are independent variables, the second term vanishes, and the partial derivative of qr with respect to some qi is nothing but delta ir, and likewise the partial derivative of ps with respect to pi is nothing but delta psi, and therefore this Poisson bracket between qr and ps becomes delta rs. So, as I said, the first term is delta IR into delta PS, which is delta RS. As I said, the second term, since P's and Q's are independent, goes to 0. So, thus the fundamental Poisson brackets between conjugate variables and between themselves, the fundamental Poisson brackets are the Poisson bracket between Qi, Qj is equal to the Poisson bracket between Pi and Pj, and each equal to 0. And the Poisson bracket between Qi, Pj is delta Ij. Now, notice that this has a similarity in quantum mechanics, where in quantum mechanics, the position, the Q's and the momenta P's are treated as dynamic, as operators. So, the dynamical variables of classical physics are considered as operators. They are raised to the level of operators in quantum mechanics, and these operators satisfy the commutation relation that Qi Pj is equal to IH cross delta Ij, and this is Heisenberg's uncertainty principle. For any other dynamical variable g which does not depend on time explicitly, that if the dynamical variable g is a function only of the coordinate and conjugate momenta, the Poisson bracket of g with the canonical coordinates is then given by g comma q I, that is the Poisson bracket of the dynamical variable g with the coordinate qi, can be easily seen to be equal to delta IR d partial derivative of g with respect to PR, which equal to minus the partial derivative of g with respect to pi, because one of the terms dg by dqi is 0. Therefore, we have the Poisson bracket of a dynamical variable g with the coordinate q as equal to minus time the partial derivative of g with respect to the momenta, and likewise the Poisson bracket of g with respect to the momentum is equal to the partial derivative of g with respect to the coordinate. Now, from the equations which I have seen earlier, we have seen that the total time derivative of a dynamical variable, namely dg by dt, is given by the Poisson bracket between the Hamiltonian and the dynamical variable g. And this we saw earlier. This is a very important result. This is the equation of motion expressed in terms of the Poisson bracket. Now, if g is a constant of motion, then obviously the derivative of g with respect to time is equal to 0, which means the Poisson bracket of h with g vanishes. So, if the Poisson bracket of a dynamical variable with the Hamiltonian vanishes, then that dynamical variable is constant in time. We will now explore the relationship between the angular momentum and Poisson bracket. The angular momentum L in terms of the canonical coordinates is given by L is equal to Q into P. In terms of components, we can write Li is equal to epsilon ijk, Qj pk, where the tensor epsilon ijk is antisymmetric between two indices, or that is epsilon ijk if all the three indices are different and the cyclic is equal to 1, which means that epsilon 1, 2, 3 is equal to epsilon 2, 3, 1 is equal to epsilon 3, 1, 2, 1, and epsilon 1, 1, 2 is equal to 0, and so on and so forth. So if you calculate now the Poisson bracket between ith and jth components of the angular momentum, that is Li, Lj Poisson bracket, that is, then this is equal to epsilon ikl, epsilon j mn, and the Poisson bracket of QKPL with QMPN. Now expanding this, expanding the Poisson bracket, we can see that this Poisson bracket along with this property of the epsilon becomes QIPJ minus PIQJ, which is equal to epsilon IJK QIPJ, and which is nothing but the kth component of the angular momentum. Thus, the Poisson bracket of the between the ith and jth components of angular momentum is equal to the kth component of the angular momentum. The Poisson bracket between the angular momentum components Li with the generalized coordinates and the conjugate momenta can likewise be calculated. So to see the Poisson bracket between the conjugate momenta Pi and Lj, that is between the ith component of the conjugate momenta and jth component of the angular momenta, the Poisson bracket Pi Lj is equal to Pi, and for Lj we have QKPL epsilon JKL, which by using the property of the Poisson bracket with Pi QK multiplied by PL epsilon JKL, and the Poisson bracket between QK and PL is delta KL, and so this becomes equal to epsilon IJL PL. And similarly, the Poisson bracket between the ith component of the generalized coordinate and jth component of angular momentum is equal to epsilon IJL QL. Now, the Poisson bracket of the product P dot Q with Lj can be evaluated, and it is found to be 0. Now, the Poisson bracket of the product P dot Q with Lj can be evaluated, and it is found to be 0. So what we have seen is that the Poisson bracket of P square, Q square, and P dot Q with any component of the angular momentum vanishes, because we have seen that the Poisson bracket of P dot Q with Lj vanishes, Poisson bracket of P square with Lj, Poisson bracket of Q square with Lj all vanishes. So, thus the Poisson bracket of angular momentum square, L square, which is equal to the sum of the square of its components, L1 square plus L2 square plus L3 square, which is scalar. So, the Poisson bracket of L square is also vanishes with a component of L. That is, the Poisson bracket of L square with any component of L square Li is also equal to 0. Now remember that in quantum mechanics, if the commutator of two operators vanishes, then these two operators possess simultaneous eigenvalues. The Poisson bracket of a component of the angular momentum with the Hamiltonian can also be calculated, and it is written as the Poisson bracket of Li with the Hamiltonian is equal to epsilon ijk qj pk with the Hamiltonian, and using the Poisson bracket expression of the momenta and the coordinates with the Hamiltonian, this can be written as epsilon ijk multiplied by qj Poisson bracket of pk with h plus Poisson bracket of qj with h multiplied by pk, and using the property of the Poisson bracket of pk with h is nothing but pk dot and qj with h is nothing but qj dot, we obtain that the Poisson bracket of a component of the angular momentum with the Hamiltonian is again equal to the time derivative of the component of the angular momentum. An important relationship which is satisfied by the Poisson bracket is the so-called Jacobi identity. For any three variables a, b, and c, the Jacobi identity always holds, where the Jacobi identity is defined as the sum of these three terms. The first term is the Poisson bracket of A with the Poisson bracket between B and C. The second term is the Poisson bracket of B with the Poisson bracket of CA. And the third term is the Poisson bracket of C with the Poisson bracket of A and B. So the sum of these three terms is always equal to 0, irrespective of what the dynamical variables A, B, and C are. The proof of this is straightforward, but a little lengthy. So what one does is that one looks at the first two terms. Then the first two terms can be expanded. That is Poisson bracket of A with the Poisson bracket of BC plus the Poisson bracket of B with the Poisson bracket of CA. First we write this as Poisson bracket of A with the Poisson bracket of BC minus the Poisson bracket of B with the Poisson bracket of AC. Then we use the definition of the Poisson bracket and expand it. And then we can see that this can be put in the form that this is a Poisson bracket of the Poisson bracket of AB with the C. These are the remaining terms can likewise be simplified, and after expanding the brackets and using the fact that during that dummy indices can be interchanged and all these terms become 0. Thus the first two terms of 8.25 and 8 become the Poisson bracket of A with the Poisson bracket of B and C as given in 8.26. Adding this to the last term in 8.25, we get the Poisson bracket of A with the Poisson bracket of BC plus the Poisson bracket of CAB. To this, we have thus proved the Jacobi identity. So Jacobi identity is straightforward to prove, but it's a little lengthy. Important thing is to remember this identity is satisfied by all dynamical variables. We will now state what is known as Poisson theorem. If the dynamical variables f and g are constants of motion, then what does that mean? That means the Poisson bracket is also a constant of motion. Since f and g are constant of motion, which means that df by dt, that the time derivative of this variable f is equal to or is given by the Poisson bracket of f with h plus a term. If f depends on the time explicitly, then plus you have the partial derivative of f with respect to t. So if they are constant of motion, then df by dt is equal to 0 and likewise dz by dt is equal to 0. Therefore, we will have the total time derivative of the Poisson bracket of f with respect to g is equal to the partial derivative of the Poisson bracket of f with g with respect to time plus the Poisson bracket of f of g with the Poisson bracket h. And if we have any three dynamical variables f, g and h, where h is Hamiltonian, then from the Jacobi identity, we obviously have the relation given in equation 8.29. Now, from the relation given in the equation 8.28, we can write the total time derivative of the Poisson bracket between f and g as shown in the slide, which we can combine terms and which can be written as finally as the Poisson bracket between the total derivative of f with respect to g plus the Poisson bracket of f with respect to the total time derivative of g, and which of course is equal to 0 from the equation 8.27 we have proved above. Therefore, the Poisson bracket of two constant of motion is also a constant of motion. Finally, we define a quantity which is called the Rauthian. Now, what is the Rauthian? We have the Lagrangian of a dynamical system which is a function of the generalized coordinates and velocities. Now, if any coordinate is cyclic, it does not occur explicitly, and the corresponding conjugate momenta is then constant. Suppose we have a system which has s number of cyclic coordinates q1, q2, qs. Then we can write L as a function of all the coordinates q1 to qn, but we can separate out the cyclic coordinates q1, qs from the rest of the coordinates going from qs plus 1 to qn. Now we construct a function r which is called the Rauthian, is then equal to pi qi dot are sum over only the cyclic coordinates minus the Lagrangian L, and when take the differential of the two sides, and when you manipulate all these things a little, algebra, not really complicated, but is lengthy. So we can write, after a little manipulation, we can write this Rauthian, this quantity, which is shown in the top of the slide as equal to total derivative of pi qi dot sum over all the cyclic variables minus the L, and further manipulations can be done, and we obtain that the partial derivative of this function r, which we have defined with respect to qi, is minus pi, and the partial derivative of r with respect to pi is qi dot. For I is equal to 1 to s, that is for cyclic coordinates, we have this, and for the cyclic coordinate, dr by dqi is equal to minus dl by dqi, and dr by dqi dot is the same thing as minus dl by dqi dot, etc. for all i's which are not cyclic. Thus, the Rauthian which we have defined behaves as the Hamiltonian for the cyclic variables. This is an important result. That is, dr by dqi is equal to 0, which is equal to pi dot, which means pi is a constant. And qi dot is equal to dr by dpi for I is equal to 1 to s. So R, the Rauthian behaves like a Hamiltonian for the cyclic variables, and for the non-cyclic coordinates, I is equal to s plus 1 to, and so on. This Rauthian behaves like the Lagrangian satisfying the Euler-Lagrangian equations, namely dr by dqi minus ddt of dr dqi dot is equal to 0 for I is equal to s plus 1 to n. Thus, when the dynamical system has both the cyclic and non-cyclic coordinates, the Rauthian behaves like a Hamiltonian for the cyclic coordinates and a Lagrangian for the non-cyclic coordinates. This is the property of the Rauthian, which one may like to remember, that when the dynamical system has both the cyclic and non-cyclic coordinates, you can define a Rauthian which behaves like a Hamiltonian for the cyclic coordinates and a Lagrangian for the non-cyclic coordinates. So, let us summarize what we have learned in this module. The first thing which we have seen, that the Poisson bracket between canonical variables are given by that the Poisson bracket between two generalized coordinates or between two generalized momenta is equal to 0, where the Poisson bracket between the coordinate and conjugate momenta is equal to delta ij. The Hamilton's equation of motion in terms of Poisson bracket are simply given by that the time derivative of the generalized coordinates qi dot is equal to the Poisson bracket of qi with h, and the time derivative of the conjugate momenta p is given by the Poisson bracket of p with h. Now, if g is a dynamical variable, and if it so happens that its Poisson bracket with the Hamiltonian vanishes, that is the Poisson bracket of g, which is any dynamical variable, with h equal to 0, then g is a constant of motion. Like, for example, if g happens to be the angular momentum square, and then which commutes with h, so L square is constant. And then there is an important Jacobi identity which holds for any three dynamical variables a, b, and c, and is given by that the Poisson bracket of a with the Poisson bracket between b and c plus Poisson bracket of b with the Poisson bracket of c and a plus the Poisson bracket of c with the Poisson bracket of ab is equal to 0.